Alright, take two for our next form of evidence. Since I'm sipping hot tea here at the late night and I have a nice little fire going beside me, I've decided to just talk in an accent the whole flaming time. So, anyway, where we were was that we had just gotten rid of the anatomy. So, we talked about homologous and analogous and vestigial structures, and then we talked about the protein and the DNA sequences yesterday. Today, we're talking about fossils, which is where bones of dead things become rocks. So, to talk about how this process works, we're going to kill one of you. I'm going to pick the lucky victim of Gavin Kenyon. So, here's Gavin. And we're going to do what we normally do with dead people. And we're going to put good old Gavin, who is dead, inside of a bloody little coffin. I mean, it's not very bloody, but it's just an expression. I'm not saying it's covered in blood. You know what I mean? So anyway, here's Gavin. He's dead, and he's underneath a hillside. And so what are we going to do with Gavin? Well, nothing. He's dead. So since Gavin is dead, we're going to let him sit there under the hillside for the dawn of time. And so years pass, and the coffin gradually gets eaten by maggots under the ground. So I'm going to draw some gross maggots. Maggots. Those are, if we're dealing with this proportionally, those maggots are just huge. Impossibly huge. So anyway, where was I? The maggots are going to eat away his coffin, so there's no more coffin. And now Gavin's dead body is exposed to the elements. And so what's going to happen is, in the ground, over time, there's going to be some groundwater that's going to seep up. And the groundwater is going to take minerals with it. So in Gavin's little cells of his body, I'm going to draw one of those little cells for you right now. Here's a cell of Gavin's body. Don't ask me why it's green, because he's dead. So anyway, Gavin's cell has fluid in it. And what fluid does naturally is it's going to evaporate. And so what's going to happen next is that the groundwater right here is going to seep into his cells. Why? Because water cycles. Once it evaporates, it's going to condense back into the cell, and it's going to keep cycling through. But the thing is that this is groundwater, or water in the ground, and water in the ground takes mineral deposits with it because it's in rock. So what's going to happen is that this water's taking rock deposits and leaving them in the cell. The rock deposits can't evaporate with the water, so when the water evaporates, the deposits stay in there. And so over thousands and thousands of years, you're going to have your cells be cast as minerals. So basically, your cell is sculpted out of rocky mineral deposits that have happened through groundwater coming inside your cell and leaving all the minerals inside of it. So basically, a fossil, which you can see in the background here, is what was once your actual bone that has since become rock through a process called fossilization or permineralization. Now, I get this question every year. So before you get carried away, if you go outside in your backyard and let's say you're Jake Reagan, and Jake Reagan goes out to his backyard and he picks up a rock and he says, "Are you my grandfather?" The answer is no! Because it doesn't happen that fast, and just because you have a rock doesn't mean it was some dead guy's head. So we're going to move on faster. Past that, we talked about how fossils happen. So the organisms are dead, they're buried, the groundwater seeps into the cells, leave the minerals behind, and then you get mineral traces that form fossil. This is our friend Archaeopteryx, which is our first fossil of a bird. And this is the oldest bird fossil, and it's evidence that birds share a common ancestor with dinosaurs. And Archaeopteryx has kind of a weird pose that looks like somebody stamped him with a rather large anvil, but we're not going to worry too much about that. And then here we have a tree that has been buried by being felled or falling over. And when the tree falls over, it's going to be buried in the ground. And when the ground buries it, It's going to have that same process of permineralization with the groundwater. It's going to seep into the cells of the wood and leave a mineral cast behind. So this is a fossilized tree. It also looks like Squidward's nose for you SpongeBob fans. Now, what we're going to do today is, how do we practice fossilization? I have a little lab for you. It's called Evolution of the Horse, and the thing about this lab is it used to involve clay, but we don't have modeling clay with us, so we're just going to have to use our imagination and draw stuff. So here's what happens. You have 4 horse ancestors over the last 50 million years. This is our earliest horse ancestor. Let's talk about Hyracotherium, which is our earliest horse ancestor. First of all, to start, it is about 0.4 meters tall, which is the equivalent of 40 centimeters, which is the size of a rather medium-small dog. So basically, you have a Chihuahua horse, or shall we call it a Chihuahua, and that is the size of a horse 50 million years ago. Kind of weird. Now, the next part about this is a horse actually 50 million years ago had 4 toes. I do not know why it starts at 2 and goes to 5, but it's got 4 toes that we can see. Toe 3 is our main toe that we see in all of the following skeletons. You can see that it's going to be the most predominantly used toe, and you can see that it gets larger every fossil, which has become a hoof over time. So this is toe 3, but over all the fossils, toe 3 has just gotten so fat that it's going to be able to become a hoof. And so the thing about this is, the next part is you have your teeth. We don't really need to worry too much about the teeth right now. And you also have the size of a horse's skeleton. So this is what 5 centimeters would look like. So this is a rather small skeleton. And nowadays, 5 centimeters would be about the size of, its ear. So the skull has gotten rather big. So what are you going to do with this here information? Oh yes, before I forget, the last part of information is going to be, what kind of habitat did it live in? So 50 million years ago, horses lived in soft, dense, moist rainforest environments. Now, they live in firm, short grass environments or prairies. So how does this all come into play? Well, you're going to use this data from Table 1, and you're going to come down to Table 2. And what you're going to do is put the information from Table 1 in Table 2 and use it to make some inferences. Let's do the first one together. So the first one is Hyracotherium, which lived 50 million years ago. So I take this information, time million of years ago that it lived is 50. Species name is Hyracotherium. You can name your firstborn child that. I know that looks like a first grader wrote it with its less dominant hand, but we're going to, move past that. Okay, the hoof print. Here's where you actually have to use your brain cells and you have to think a little bit. Sorry in advance. What you do is you go up here and you go to Hyracotherium and you look at its toes, all right? What I want you to imagine, and this is actually how it's standing, is it's kind of difficult to imagine how this is standing. So the way you can simulate this is you can take your fingers, all right? And I'm going to draw what you would do with your hand. How do I get this flaming thing off the bloody screen? There we go. So what you're going to do with your hand is I'm going to draw a wrist, okay? So here's your wrist. And you're going to take your thumb, you're going to leave it up here. I know it looks like a mutant hand, but bear with me. And then you're actually going to put your finger, and you're just going to put your finger down so you can put a fingerprint like that, okay? Then you're going to do the same thing with the other fingers, and I'm going to draw your third finger and your fourth finger. And so you have basically 4 little spots where you would put your fingers. And that would be what this hoof print of Hyracotherium would look like. Why? Because it's got 4 toes and it's standing on its very tippy toes, like you would put your fingers on the very tips of your fingers and stand up like that. So we're going to get rid of that, and we're going to go down here and draw the hoof print. So since Hyracotherium had 4 toes and they were standing right up on top of the tippy toes, we're going to draw what the hoof print would look like if you saw it in the sand. So you would have a toe here, a toe here, a toe here, and a toe here. So basically, if you were following this thing around, stalking it, hoping to kill it and eat it, since it's the size of a Chihuahua horse, you would see this footprint in toe, all right? So this is what the toes would look like. Now the habitat, you just list what it tells you up here. So it was soft, dense rainforest, okay? So we write that, soft, dense rainforest. And the height is 40 centimeters. It says in meters here, so that would be 0.4 meters. And then the proposed advantages. Again, you have to think and use them brain cells. Sorry in advance again. What are some advantages for surviving in this type of a habitat if you're small, the size of a dog, and you have 4 toes? Well, if it's soft and you have a giant hoof instead, you're going to sink right through that soft ground, and you're not going to be able to get very far if you sink. So you might write that down. Won't sink. What's another advantage? You're small, so and you're in a rainforest. If you ever look up a picture in a rainforest, you're going to have vines and stuff and trees, and you got bushes. There's just mass chaos everywhere, and it's hard to get through. So if you're a horse and you're the size of a modern horse, which is, about 1.6 meters tall, then it's going to be very hard to get through this stuff. So you actually want to be small so you can move easy. And there you go. There's a good start. What are some disadvantages of being a horse in this type of habitat? Well, if you're small and the size of a Chihuahua dog, you're going to not be a very fierce predator or prey for that matter. So what that means is if you're being chased, you're not going to be able to fight. And also, because you're the size of a small dog and you have 4 toes and you're living in a rainforest, you're probably not very fast. Okay, so those are some disadvantages there. All right, so what I want you to do is for the next 3, I want you to look at this data. I want you to mainly focus on what kind of footprint does it have? Where is it living? Okay, how big is it? So we get a little bigger here. And how are these characteristics going to allow it to survive in this habitat? Now, when you're done, you're going to have to come down here and you're going to have to tell me whether or not you think a modern day horse, the one living present day, would be able to survive in the rainforests of 50 million years ago. And once you get through this chart, you'll be able to give me a pretty good judgment on whether or not you think it would be able to survive 50 million years ago. All right. The next thing is, from the fossil evidence, you'll have to tell me which toes were vestigial. And you'll tell me that by observing which toes receded over time. So if you look up here and you look at the 4 feet, which toes seem to be getting smaller, those would be vestigial. And then you're done. When you're done, you just submit it to the link on Canvas. And I hope you have a lovely Thursday and a fantastic weekend.